So we've seen logistic regression, and we know that there's an issue with having to assume linear separability. We can get around that by actually mimicking what our own brains do, and thus we're going to start looking at artificial neural networks. Neurons and neural networks. Our brains make decisions using neural networks, and we don't have to require linear separability. We're not going to get a perfect model or even a very good model of how our brains work, but even the crude model we get is going to be highly effective. So this is a neuron. It has these components: dendrite, soma, axon, and synapses. Signals propagate from the dendrites to the soma, and they tend to decay if they're below a certain threshold. On the other hand, we could have signals arriving in such a way as to cause action potentials. So the signals arrive at the soma, and in sufficient quantity and closeness to each other to cause a threshold to be exceeded, causing a neuron to fire, sending a signal along its axon and out to other neurons. The signal itself is electrical, and it has a membrane depolarization starting at -70 millivolts. There is myelin that acts as an insulator, but there are breaks in the myelin, as you saw, and at the breaks we're going to see rapid depolarization at the breaks, so that in reality the propagation is electrochemical, not just electrical. So we get a reversal in polarity at each one of these breaks, and this coordination between the electrical and the chemical, the ion populations at the breaks, is what causes these action potentials, and they can propagate very quickly. So an action potential is related to the opening and closing of sodium channels and potassium channels. So we have these charged ions, and crossing a threshold means that we have a opening of many sodium channels, and then they close, and we get a restoration when the potassium channels open. Now this led to 5 articles in 1952 by Hodgkin and Huxley with a man named Bernard Katz. They modeled the dynamics of these ion populations, and their model, they showed, produces action potentials. And in 1963, Hodgkin and Huxley won the Nobel Prize in Physiology for deriving the Hodgkin-Huxley Equations, and they're now the foundation of the study of excitable cells such as the neuron. So here is Hodgkin and Huxley, and here are their equations. Notice they're pretty complicated. As a matter of fact, they didn't even come close to solving them. It was really, they won their Nobel Prize just for deriving them. And in fact, the Hodgkin-Huxley equations are nearly intractable, which means almost as soon as they were discovered, researchers began developing artificial models to better understand, in particular, the Hodgkin-Huxley equations. And the goal is simpler models that, in some sense, qualitatively, holistically, resemble real-world models. So we're going to do the same thing. So what does a neuron do? Well, it takes signals from other neurons, and if the signals cooperatively are strong enough, then we get a signal sent down the axon, which means it goes out to other neurons. Here are the variables we're going to be looking at. We're going to have an output variable from the jth neuron, an interior or a state variable, S of j, for each neuron. And then we're going to have connections between the ith neuron and the jth neuron, and those are going to be synaptic weights. And then we'll have a threshold, theta sub j, and then there's going to be a firing function, which will be very important, as we'll see momentarily. So an artificial neuron, again, here are the variables. It collects with weight w sub ij signals from other neurons, and the sum of those gives us some kind of internal state. And then if the internal state is high enough, it exceeds the threshold, then we have a signal that goes out according to the firing function. Let's look at the firing function. Output signals do not vary much in strength or in amplitude. So here you can see a pulse train of action potentials. They're all about the same magnitude. So in some sense we can say that our firing function should have essentially two values. It should rise up to a maximum, and we're going to just call that 1, and it should descend to a minimum, which we're going to say is 0. So firing functions will also be sigmoidal. Sigmoidal, which means they monotonically go from a low up to a high, in this case 0 to 1. The one we'll look at most of the time actually should look kind of familiar. It looks like logistic regression. And so it's this firing function that we get sigma of s sub j minus theta sub j, 1 over 1 plus e to the negative kappa sub j, s sub j minus theta sub j. And as we change kappa, we get a more rapid jump. And so we can say, well, in the limit, we can have a discrete case where we monotonically go from 0 to 1 by jumping at a certain threshold theta sub j. And notice we're going from 0 to 1 primarily to relate things back to what we've already done, but we can actually go from any number to any other number. And we're soon going to be going from negative 1 to 1. So let's look back at our artificial neuron. We have a collection of signals coming in, and those are summed with weights given by the synaptic weights to give some internal state, and then we get a firing function producing a signal out. So the signal out is sigma, the firing function, acting on the sum wi sub j x sub j minus the threshold, which is theta sub I. And so that looks something like this. I've suppressed the kappa, or set the kappa equal to 1, just so you can see the form, that it looks an awful lot like logistic regression, where logistic regression could be the case where kappa is equal to 1. And in particular, that exponent is linear. So again, this is just the logistic regression model with kappa equal to 1. And so we have a close relationship between neurons and our logistic regression, which we were kind of hoping for. We'll often use matrix notation. So we'll use, instead of a sum of a product, we'll use a transpose, a row times a column. And so we can write this more compactly as the firing function acting on the transpose of the synaptic weight vector times the input vector minus the threshold. So logistic regression is just an artificial neuron with a special choice of kappa equal to 1 in some sense. So an artificial neuron, just all by itself, is a linear classifier because it's logistic regression. But real-world neurons likely are not linear classifiers. So we're actually looking at an artificial neuron that is actually not quite what a real-world neuron is, but it does allow us to do something very nice. It allows us to relax this big assumption of logistic regression solely as a linear classifier. You might ask, well, how can that be if the artificial neuron is also a linear classifier? Well, the answer is that real neurons form networks. And so we have inside the network signals flowing from neuron to neuron on a regular basis, in particular from the moment we're born till the day we take our last breath. We have neurons sending signals to neurons. So we're going to look not at artificial neurons per se, but at artificial neural networks, which we'll abbreviate ANN. They're made of artificial neurons, and each neuron sums inputs from other neurons, applies a firing function to the sum, and it weights using synaptic weights, W sub ij. These correspond to the weights in logistic regression, and so we can interpret these weights via log odds and odds. And we can use biology to interpret the synaptic weights and the artificial neurons. So let's do that. So the biology first tells us that a synapse could be interpreted as either inhibitory or excitatory. That's not something we can get from logistic regression. Also from the biology, we know that we should use networks with high genus. When you look at, in the lab, neural networks made up of actual real-world neurons in some cases, but they're planar. They're connected in a two-dimensional network. They're not very smart. They tend to be sort of stupid. So we really need networks with high genus. And unfortunately, that's about it. The network topology in anything but the simplest organism is so elaborate, we currently can't even study it. It's so difficult to classify. We do study it in a very large sense as an organ. We study the brain and parts of the brain. But the actual topology with neurons forming vertices of this elaborate network, it's beyond us right now. Except, of course, there are some very simple organisms, like C. elegans, where we can actually look at that network topology. And it's interesting to note that we find that C. elegans' neural network tends to be small world. Also from the biology, we know that a real-world neural network has an associated energy that dissipates as it thinks. And our brains do the same thing. And CPUs in a computer, same thing. We burn huge amounts of energy just due to our brain. Our brain's only 2% of our body weight, and yet requires 20% of our resting metabolic rate. And if we're doing intense learning, then that burns the most calories. It actually turns out that intense thought, where we're just problem solving or doing other things where we're not really incorporating new information, that really doesn't burn that much calories. But learning, where we're forming new synaptic connections, that really burns the most calories. Now the brain is too complex beyond these things to imply anything additional. So we can't really get exactly how the brain works by looking at the biology. So instead we're going to use math. And in particular, we'll get much of our theory from the math. We'll motivate most of our network structures from mathematical motivations. They won't even be small world. And our algorithms will be mathematically motivated. We'll take advantage of the energy thing mathematically. It'll be dissipative, but not in the same way that we get dissipation of energy from the biology. And in particular, we'll tend to use the energy more often statistically. So in summary, artificial neurons mimic real-world neurons. They sum and fire, or sometimes we say integrate and fire. Individual neurons are essentially logistic regression machines. And remember, this is artificial neurons are logistic regression machines, not necessarily real-world neurons. Artificial neural networks mimic real-world networks as much as possible. However, we're going to find out that these artificial neural networks are actually more mathematical than biological. Although the more we know about the biology, the more we can use math to improve our neural networks.